Welcome to the brave souls who have come out on this cold night. I just committed myself to reusing these lectures in the summer school, and as you folks suggested, doing the sections myself and putting them on video. So there will be people watching this in mid-July, and they might like to see that the way I got here was by wearing this nice vest, which I bought once when I was in Alaska. And I assume that many of the people here did things the same way. Tonight I'm going to devote to random walks and a lot of curiously simple results that I can prove without any calculation. I'm not saying the proofs are easy, but they're non-calculational proofs. To start, though, I would like to show you some of what I'm going to be attempting to prove. And this is my mock-up for the second computer project. The second computer project seemed to work okay last spring, so it's true the version that's online now still has last spring's revision date, but I'm unaware of any changes that need to be made for it. And after tonight, if you're feeling ambitious, you can get started on it. I clicked on Easy PHP, and you can see a red dot flashing there, which means my Apache server is running. When I tried this out before class, I got numerous messages that it had encountered an error and needed to shut down, but I will hope for a little bit better luck now. And in order to show you the project I've created, I'm just going to start up Netscape and bring up a local URL. If you look up there, you'll see this is HTTP localhost randwalk index, and that means that the web page we're looking at is being generated right on this computer. And here are some examples of random walks with a lot more steps than I could generate without the aid of a computer. And when you look at them, you'll see that a surprising number of them sort of drift away from the origin and don't come back. Look at that top one. You'd say that sort of thing looks rather unlikely. Here are lots more of them. Some go up, some go down. And here is the only one that does what I think most people might expect the typical random walk to do, to drift back and forth from one side of the origin to the other. I think most people fondly imagine that if, say, Harvard and Yale, evenly matched teams, played lots and lots of games, that Harvard would be ahead roughly half the time, Yale would be ahead roughly half the time. And what I'm going to show you tonight is that really nothing could be further from the truth. The truth is exactly the opposite of what you would guess. What I've done here is to generate some statistics. For some of these, I'm going to be able to prove in full detail what we expect to happen. For others, I've decided, in one case, just today while preparing tonight's lecture, that I want you to know the result, but the proof is sufficiently messy that let's leave it at knowing the result. So here are some sample statistics, and I assume, can I be seen if I point at the screen here? Okay, so things we can look at. The final level in which the random walk ends up, and that's really easy to calculate because up steps and down steps each happen with a probability of 1/2. So that's a simple matter of a binomial distribution. Another thing we can calculate is out of 300 steps, the last time the random walk was ever in level 0. That might mean if Harvard and Yale play 300 games, the last time the series was tied was 14 games into the series. And what I'm going to show you is that the most likely outcome is that this last 0 will occur right before the end or right after the beginning, and the least likely place for it to occur is where you'd look at it, namely right in the middle. I can also count the number of times that Harvard is ahead, the number of times that Yale is ahead, and the number of times the series is tied. And you might have guessed that if the teams are evenly matched, Harvard would be ahead roughly half the time, Yale would be ahead roughly half the time. Though I won't be able to prove this, or sorry, I could prove it, but I won't prove it out of consideration for you. The proof is in the notes. I can actually show that the most likely outcome is that one team or the other is ahead most of the time, and the least likely outcome is that each team is ahead half the time. We can also ask, when does the random walk first achieve its maximum value? Again, it's most likely to do that very early on or very late on. And you can also ask, when is the first time that Harvard is as far ahead as it's going to be at the end of the series? That turns out to be the same problem as the last zero problem. If I hit reload, I get a bunch more random walks. And it's worth looking at this just to get an honest idea of what these things look like typically. Okay, now I want to say a little more about topic 10 from last time, which was expected lead times, because I did this rather hastily, and this provides me with an opportunity to review the ballot theorem and hitting time theorem, which in my opinion are two names for the same theorem. So here's a general way of looking at this situation. You got a random walk, level 1. You got another random walk, level 2. This is Anna putting lots and lots of money on red at the roulette table, figuring if she does that, she'll either lose all her money and get to go back and study for the GRE, or she'll win so much money the only sensible thing to do is to cash out. And what the theorem proved last week says is the following. First, we have the ballot theorem. The ballot theorem talks about paths that go from level 1, you're starting to count the votes, and end at level 2 without the eventual winner in the election ever going behind. Or if you want to think of this as a sports metaphor, this is a Harvard-Yale series where Harvard wins the series, and after the first game, the series never even gets tied again. So I'm going to mark this yes ballot. Here's another path that gets to the same place. And that's a no for the ballot theorem because the eventual winner is sometimes behind, but that's a yes for the hitting time theorem. The hitting time theorem talks about cases where the eventual winner only achieves his or her final lead after the very last vote is counted. So this is yes for hitting time. On the other hand, this one is no for the hitting time because the eventual winner got further ahead and then fell back. And there are a handful of paths like this that are yes for both. And I fooled around with this. There's no simple formula for how many of these there are. You have to count them directly if you're interested in knowing. Okay, so what the theorem says is that the fraction of paths not crossing level 1 or the fraction of paths not crossing level 2. Pick level 1 or level 2 depending on whether you want the ballot theorem or the hitting time theorem is equal to the difference in levels, which I'll call B, divided by the number of steps, which is equal to n. So you take the magnitude of the change in level, divide by the number of steps over which that occurs. That's the number, that's the fraction of the paths that either, take your choice, fail to recross the original level or fail to recross the final level. And the reason this works is basically the whole situation is symmetric with respect to whether you go forward or backwards, whether you count or uncount the ballots. Okay, now exploiting this fact last time, and I'm going to erase this because I'll need all my space, I quickly proved the following remarkable and, at least to me, rather counterintuitive result. We have, let us say, a football series, and the deal is that this series goes on until it's tied again, whereupon it ends. It could, in principle, end after just 2 games if Harvard and Yale split the first 2 games, or it could go on for a very long time. And the rather remarkable result is this. If you say, as an extension student, I would like a free ticket whenever Harvard is R games ahead, your expected number of free tickets is independent of the value of R that you choose. And it seems very, very strange that you have an expectation of getting as many free tickets if you say, I want a free ticket whenever Harvard is 100 games ahead, as if you said, I want a free ticket whenever Harvard is 1 game ahead. But that's what I proved last time, and the proof is extremely simple. What we do is look at this quantity, which following the book that I called F sub R of n, and because the ballot theorem and the hitting time theorem are the same thing, this is equal to 2 different things. This is, on the one hand, equal to the probability that H is ahead by R games for the first time after n games, and it's also equal to the probability that H is ahead by R games after n games and there are no ties yet. Because this says we're talking about a path that satisfies the ballot theorem. It never recrossed the Harvard and Yale are tied line. This, on the other hand, is saying Harvard is this far ahead for the first time. That's the hitting time condition, that this is the first time ever that Harvard has been R games ahead. The graph representing the random walk has never crossed the R games ahead line. Does everyone see that these are 2 equivalent interpretations of the same thing? And so, when I sum this up, to infinity, this is, on the one hand, equal to the probability that Harvard is ever ahead by R games, because clearly the probability that Harvard is ever ahead by R games is equal to the sum of the probability that it's ahead by that many after precisely R games, or R plus 1 games, or R plus 2 games, and so on, up to infinity. but this is also equal to the expected number of free tickets, because that's equal to the probability that you get a free ticket after R games, after R+1 games, after R+2 games. And as long as the series has not yet been tied, if the random walk is at level R after a certain number of games, you get a free ticket. So we've got this remarkable result that the expected number of free tickets is equal to the probability that Harvard ever gets R games ahead. And if Harvard is a better team, or if Harvard and Yale are equally matched, that probability is 1, and the expected number of free tickets is 1. Now, what I'd like to do that, yes?
I was actually confused about that part, because it's not 1 if, it's 1 if you can go down as far as you want and then come back up. But in this case, we stop if we go back to 0. Not sure what I'm missing.
I think I see your point. No. It's the probability that Harvard will ever be ahead. We're not talking ballot theorem here. We're talking hitting time theorem. Ties don't stop it. The sum of these quantities is the probability that if the series is played forever, not stopping when there's a tie, that Harvard will eventually have an R game lead. And by the gambler's ruin result, that probability is 1. Remember, I proved that if you start with R dollars in a casino and play on without quitting, no matter how far ahead you get, the probability that you will get back to level 0 and go broke is 1. So you had me thinking for a minute, but in this case, we're talking pure hitting time theorem. I'm not saying this is the probability that Harvard will get ahead by R games with the condition that the series ends on a tie, because in that case, you'd be guaranteed at least 1 ticket, and you'd probably get more. This is the probability that if the series just goes on and on without the ending condition, Harvard will eventually be ahead. Catherine, you look puzzled. You had your hand
No,
up.
I just need, I think I'm okay.
Okay?
Yeah.
It took me a long time to understand this result, so it's reasonable to be puzzled. Other questions about this? Well, look, let me do my special case. This is one of these situations where the easiest special case is messier to analyze than the general case. But I still like to work out special cases when I see a general result whose proof seems too easy to be true. That's really the problem with this. This is a counterintuitive result, and the proof is basically one line and no calculation. You say, we add these things up, and these two quantities, which on the face of it don't appear to bear any relationship to one another, turn out to be equal. So let's choose R equals 1 and look at the details. Okay, so you say to the extension football office, I want my free ticket whenever Harvard is 1 game ahead. Yale wins the first game. How many free tickets are you ever going to get?
None.
None, because the series will bet tied before Harvard ever gets a chance to be ahead. So this happens with a probability of 1/2, and you get no free tickets. Well, there's a 50% chance that Harvard will win the first game. But what's the probability that that will happen? Harvard wins the first game, Yale wins the second game, and the series is over. How many free tickets do you get?
1.
1. So you're only going to get more than one free ticket if Harvard wins the first 2 games, right? And somehow this case, which has a probability of 1/4, has to bring the expected number of free tickets up to 1. And the only way that's going to happen is if you get an expectation of three free tickets if Harvard wins the first game. So let's think about this. Okay, Harvard is a game ahead. Sooner or later, Harvard is going to be 1 game ahead for a second time. So with probability 1, after a while, this will come back to here. So there's 1 free ticket. You're guaranteed to get at least 2 free tickets. And then you may get more free tickets if Harvard wins the next game. Yeah, Jerry?
That's an application of Gambler's Ruin now.
Yes, this is an application of Gambler's Ruin.
Starting at 1.
If you start at if you start at 1, the probability that you will come back to 1 is also 1. Basically, what Gambler's Ruin says is if you never quit, no matter what level you start at, and no matter what level you want to reach, if it's a perfectly fair game, the probability that you will eventually get there is 1, though it may take a very long time for that to happen. Okay, so how many free tickets? The case 3 is Harvard wins the first 2 games. After Harvard wins the first game, you get a ticket. After Harvard wins the second game, you know that sooner or later, Harvard's lead is going to go back to 1 game and you get your second free ticket. And then either Yale wins and that's all you get, or Harvard wins again and you say, now I'm set up for yet another free ticket. So I just introduced the symbol capital W to mean the expected number of free tickets that you'll get after the first 2. So W is the number of free tickets that you expect to get under circumstances where Harvard has a lead of 1 game. And we can easily figure out what W is. Harvard's 1 game ahead. What's the probability that Harvard will win the next game and you'll be in line for more free tickets? A half. If Harvard goes 1 game ahead, how many more free tickets are you going to get? Well, you're sure to get 1, and then you're in the same situation that you started out with, and you'll get 1 more. Another nice example of taking something that's intrinsically infinite and turning it into an equation. Everyone see that this is the right equation for W? And this is very easy to solve. This says W equals 1/2 plus 1/2 W, or 1/2 W equals 1/2. So W equals 1. And the expected free tickets is 2 plus W, which is 3. So everything checks. In the case where you choose to claim your free ticket when Harvard is 1 game ahead, a quarter of the time you'll get 1 free ticket, a quarter of the time you'll get an expected number of free tickets equal to 3, and the expected number of free tickets in all is equal to 1. Now, if you pick R equal to 2, life becomes much more complicated. The only way you're going to get any free tickets if you pick R equals 2 is if Harvard wins the first 2 games. Because if Harvard doesn't win the first 2 games, the series got tied before Harvard ever got 2 games ahead. And this happens with P equal to 1/4. But you see, if this ever happens, then you're really likely to cash in. Because now you're in a situation where even if Harvard loses the next game, they might come back and tie it again. And in that sense, it's a little bit misleading just to point out your expectation is the same no matter what value of R you choose. If you choose R equals 1, a quarter of the time you'll get a free ticket, another quarter of the time you'll get lots of free tickets. if you choose p equals 1/4, the probability of getting any free tickets at all goes from a half down to a fourth. But if you start getting free tickets, you're really likely to cash in. And if you pick r equals 10, the probability that you will get any free tickets at all is negligible. But if you ever get that first free ticket, now you've got this series where Harvard is 10 games ahead, and you will start collecting a free ticket every time Harvard is 10 games ahead until, as is guaranteed by Gambler's Ruin, Yale finally, although the teams are evenly matched, wins 10 more games than Harvard. So while the expectation is the same, the variance, if you choose a large value of r, goes up, up, up. If you want a modest chance of getting a couple of free tickets, you choose r equals 1. But if you say, what really matters to me is I would like to bring every friend and relative that I have in the whole world to a Harvard football game, then you say pick r equals 20, and if you get any free tickets, you probably get almost enough free tickets if you save them up to fill the entire Harvard stadium. Okay, that was cute result number 1. Now, in order to do the lemma that's behind the rest of the cute results, I have to return to one of the words in the title of this course, namely counting, and talk about bijections between paths. And I should say, some of the things that I'm going to prove by purely counting arguments with no calculation are proved in the textbook by so-called combinatorial arguments, doing lots of algebra with binomial coefficients. I stumbled across this approach in the classic probability text by Feller, and Feller must have thought very highly of this, because one of the flaws of academics is we're very fond of telling our students, cite your sources, cite your sources, cite your sources. But how often do you see an instructor who cites a source for a homework problem? And this is one of the few cases where in a textbook I've seen a source cited for a problem. Feller says, I believe it's W. Nelson who is responsible for this problem. Well, what did I do with this problem? I reassigned it as homework with attribution to Feller, having reassigned it, having attributed it to Nelson. So I'd given the problem I knew as homework, and I had to dream up another example so you could figure out how to do this. So this next algorithm, while I'm sure I'm about the 1,000th person to think of it, is one I dreamed up on my own, so I don't have to cite any references for it, and you can probably do it the same. Here's the basic result I want to show. This is one of the most remarkable results in all of mathematics, in my opinion. We've got a random walk with 2n paths, and there are 3 classes of paths we might identify. That I'm going to characterize as a return to 0 path. Harvard and Yale play 2n games, and at the end of 2n games, the series is all tied up. Here's the sort of path that I'm going to characterize as a non-zero path. Either Harvard or Yale goes ahead at the beginning, and the series never gets tied. And finally, here's a type of path that I'm going to characterize as a non-negative path. Harvard goes ahead, and from time to time the series gets tied, but Yale is never ahead. Now, the incredible result is there are exactly the same number of paths of this type as of this type as of this type. And there are two ways of showing this. The way that's done in the textbook is basically to count each of them independently using binomial coefficients. This works perfectly well, but it's rather messy. A more elegant way of doing it is to show that there is a bijection among the three types of paths. That given a path like this, you can turn it into a path like this and into a path like this in an invertible way. And so the set of these paths is in one-to-one correspondence with the set of these paths, is in one-to-one correspondence with the set of these paths, and even if you didn't know how many paths there were, though it's perfectly easy to work that out, you'd get the same. Before I do this, I'm going to show you that this is true by considering a four-game series. I'm going to call this case 3, case 1, and case 2 for reasons which will become apparent later. And let's write down all the ways that Harvard and Yale can play 4 games and come back to 0. Maybe Harvard wins the first 2 and then Yale wins the next 2. Or you could have Harvard, Yale, or Harvard, Yale, Yale, Harvard. Or alternatively, Yale could start out ahead. Y, H, and finally Y, H, Y. And you say, this is obvious. This is precisely the number of ways of getting precisely 2 H's and 2 Y's when we have 4 games between Harvard and Yale. So in this case, it's clear that 6 of the 16 possible outcomes of this 4-game series are a return to 0 path. This one is not so obvious. Let's look at the non-zero paths. Well, here's an obvious one. Harvard wins all the games. Or Harvard wins the first 3 games and Yale loses. Or Harvard wins the first 2 games and Yale wins the third, but Harvard comes back to win the fourth. Those are the 3 ways that Harvard can be forever ahead. And then there are the 3 inverted cases where Yale goes ahead and never looks back. 6 of these and 6 of these. And it's not at all obvious, I would trust, that there should be just as many of these as there are of these. And finally, the non-negative ones. Well, how can that happen? Well, you could have Harvard go ahead for good. Harvard has to win the first game all the time. Here, Harvard could win the first 3 games, and then Yale could make a minor comeback. Or Harvard could win the first 2 games, and then we have a Yale win and a Harvard win. Or Harvard could win the first 2 and Yale the next 2. That's okay as a non-negative path. It ends up tied, but that's okay. Non-negative just means Yale is never ahead. And there are going to be 2 more like this, H, Y, which looks like that. And then I just have to think of the one more that I have overlooked.
HYYH?
No, HYYH.
No.
Yale has gone ahead. There's
All right.
HYHH. Thank you. Okay? So 6 of these, 6 of these, 6 of these. And my claim is this is a general phenomenon. It's more work to enumerate it if there are more games, but they're always the same number of these, as of these, as of these. And what I want to do first is prove that the number of paths for case 2 is equal to the number of paths for case 1. And the way I do that is by showing you how to turn one of these paths into one of these paths in an invertible way. Because that's the test for 2 sets to have the same size. If there's a bijection, an invertible function between them, then the 2 sets have the same size. Okay, so what I want to show you is that each all positive path gives rise to two non-negative paths. This is very slightly different from the argument I put in the lecture outline, but I decided this is a slightly easier way to express the idea. So what I need to show you is that given a path where the series is never tied like that, I can make out of that two paths where Harvard is never behind. The all positive paths are half the non-zero paths. So what I'm claiming is that out of half the non-zero paths, I can make all the non-negative paths. That shows the total number of non-zero paths is equal to the total number of non-negative paths. Okay. And this one is really quite easy to do. If we have an all positive path, Harvard has to win the first game. So what we can do is say, we're only going to start counting after Harvard has won the first game. Now, if Harvard won the first game, we still have an all positive path, even if Harvard is only one game ahead later on. And so we have a path that starts here, and if you view it as relative to this zero level and this starting position, it's a non-negative path, and it goes through 2n minus 1 steps, which is odd, right? Now, if Harvard and Yale have played an odd number of games and Harvard is ahead, what is the minimum Harvard lead? 1, okay? Two teams can't be tied if they played an odd number of games. So at the end of this, Harvard must be at least one game ahead. And that means we can tack on either a Harvard win at the end or a Yale win at the end, and we get two different paths where Harvard is never behind, may be tied but never behind. And furthermore, if we want to go backwards, all we have to do is take one of these non-negative paths, remove the last step from it, and go backwards. But if we have an up step, we can agree to flip it over and get the kind of non-zero path where Yale goes ahead to stay. So this is basically a pure counting proof that the number of non-zero paths is equal to the number of non-negative paths. I take a Harvard ahead non-zero path and I turn it into two non-negative paths. I take a non-negative path, and depending on whether the last game is a Yale win or a Harvard win, I either turn it into a non-zero path where Harvard goes ahead forever or into a non-zero path where Yale goes ahead forever. Everyone comfortable with this? You'll need these ideas to do the homework. The homework problems look baffling initially, but they yield to this sort of obscure knowledge. And this is obscure knowledge because I proved this, but it's still not obvious to me. You know, it's still a remarkable result, even though I can prove it with a paragraph of argument. Okay, that was the easy one. Now I'm going to go on to topic number 12, which I have called another bijection. And this one, as I said, I invented myself. And I was sufficiently wary that I did what I regard as a reasonable test when I think I have invented a bijection. That is, when I think I've invented an invertible function. What I do is write a computer program, and how do we get this to project again? Do I have to do something magic?
Screen asleep.
Ah, there we go. Okay. So, here is a technique for starting with a series that's tied after a certain number of games, converting it into a series where either Harvard or Yale is always ahead using one function, and then using another independently written function, inverting the process to get back exactly what I started with. So this is a computerized demonstration that I've got a bijection. Starting with any path like this, which returns to 0, I can convert it into one like this that never touches 0 again, and I can convert it back and get the original path. I have hard-coded the paths I put into here, but I've got a couple of other examples. Here is one where in the original path it is Harvard that has the largest lead. That converts into a path where Yale is always ahead, and it converts back into the original path. And here is one with a lot more steps. But this is a computer implementation of what I am going to now show to you on a theoretical basis. So what I want to do is to start with a non-zero path and find what I'm going to call the maximum excursion. The maximum excursion is the absolute value of the largest level achieved. If Harvard at some point is 4 games ahead, the maximum excursion is 4. If Yale at some point is 5 games ahead, that is, Harvard is minus 5 games ahead, the maximum excursion is 5. And if there's a tie, if there's a time when Harvard's 4 games ahead and another time when Yale is 4 games ahead, I'm going to pick the one that happens first. So I'm interested in finding the first place the maximum excursion occurs, and the path I want to use is the one that's illustrated in the notes. Harvard wins the first 2 games, and then Yale wins 5 in a row. And after that, Harvard wins 4 in a row. And Yale wins the final game. And if you count this up, you'll see there are 6 Harvard wins and 6 Yale wins. So this ends up in a tie. And we can make a little graph to represent it. Harvard wins 2, Yale wins 5, Harvard wins 4, and Yale wins the last game.
Is this supposed to be coming directly out of our notes? Because that's
This is
different
not
than
what
what
you
we
have in
have.
your
Okay, this is a simpler one that's in there.
I don't know. We have 2 Harvard, 5 Yale, 1 Harvard, 1 Yale, 3
Okay,
Harvard.
this is a different one.
Okay.
So good, you've got 2 examples.
Okay.
I forgot that I changed it, but this is equivalent to the one in the notes. Okay, so here is how I want to break this up. I want to split off the single game before the maximum excursion occurs. Okay, everyone see that that's easy enough to do. And I'm going to call that number 1 because that's going to be the first part of the reconstructed path. And then number 2 is going to be everything that happens after that. And number 3 is going to be everything that happens before that. So I have broken the path up into pieces that I have numbered 3, 1, and 2 respectively. And now I'm going to reassemble these pieces to convert this path, which has the property of returning to 0, into a path that can never touch 0. Jerry, you've got a question?
No, I didn't understand your notation. Now I do.
Okay. So, here's how I'm going to do this. One prime is number 1 flipped over, which means h turns into y and y turns into h. So in my new path, since part 1 here was a Yale win, part 1 prime has to be a Harvard win. So in the case where the maximum excursion is negative, Harvard is going to start out ahead. After this, Harvard is going to be 1 game ahead in this specific case and also in general. Part 2 prime is exactly the same as 2. So what I'm going to do is now tack on h, 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 y. So in the case where the maximum excursion is on the negative side, Harvard's going to jump off to a lead, and then this is guaranteed to put Harvard even further ahead because this is the part of the original part of the original path that took us from a Yale lead back to a tie. So in this case, Harvard gains 3 more games. But if I call this negative k more generally, which in my example is negative 3, in general, in this part, we're going to go from the maximum Yale lead up to a tie. And so Harvard's going to gain k games here. Okay. So now Harvard is k plus 1 games ahead. I still have to deal with part 3.
What is K again?
K is the maximum Yale lead.
Okay.
Okay? And in my example, the maximum Yale lead is 3 games. So, sorry, K is, what's the right way to put this? K is the negative, no, K is the maximum Yale lead. K is plus 3, because Yale goes 3 games ahead. Okay. Number 3 prime is 3 traversed backwards. In other words, traversed in a way that it would take us from here to here. So Harvard is starting with a 2-game deficit. In order to get to a 1-game lead, what do we need? We need some Harvard wins, don't we? So to make 3 prime, I take 3, I write it backwards, and furthermore, I change y's into h's and h's into y's. Here we start with a situation where Yale is 3 games ahead. With 4 h's, we turn that into a 1-game Harvard. Whoops. Sorry. We start with Harvard being 2 games behind. With 4 Harvard wins, Harvard is 2 games ahead, and then 2 Yale wins brings us back to the beginning. Everyone comfortable with this? So that's exactly what I have done over here. If you look at this, here is the maximum Yale lead. Here is 1 prime, and then I've tacked on to that a copy of this bit, which is here, and then I've run this backwards, going up and zipping down I've turned it into that. So this is a computerized version of exactly the algorithm that I've got. In this particular case, Harvard starts with a k-1 game deficit and ends up at 0. So Harvard will gain k-1 games. In this part, it'll take us from Harvard 2 games down to 0. In this particular case, it's 2, and Harvard ends up 6 games ahead here with 9 wins and 3 losses. But in general, Harvard will end up 2k games ahead. And since this only applies in the case where Yale is eventually at least 1 game ahead, this is guaranteed to get us to level 2. And furthermore, there's no way that we can get down to level 0 because Harvard is 2 games ahead here and breaks even here. So this is guaranteed to turn a path that returns to 0 into a path that never touches the origin again. And now, of course, we put the first case and the second case together and say, now we've got it all. We've shown that the number of non-zero paths is equal to the number of non-negative paths. We've shown that the number of return to 0 paths is equal to the number of non-zero paths. And it follows that both of those are equal to the number of non-negative paths. So I showed you initially an example of this with just 6 games, but I've now proved it completely in general without writing down a single binomial coefficient. Just by showing you how to convert one of these paths into another, I've shown you that the number of return to 0 paths equals the number of non-zero paths equals the number of non-negative paths. And how much time have I got left? I've got almost 10 minutes, I got 8 minutes. And yes, Jerry?
I'm interested in the function that converts it back.
Oh, yes. The function that inverts it.
You do all those things in reverse order, yes?
Thank you. The function that reverses it works like this. Let's start with the path I got, and I want to show this both as a string and as a graph. The example I was doing was a Harvard win followed by 1, 2, 3, 4 Harvard wins and a Yale win followed by 4 more Harvard wins and 2 Yale wins. So this is H, 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 Y, H, 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 Y, Y. This is 3 prime. This is 2 prime. This is 1 prime. The only tricky thing is finding this dividing point. And here's how you do it. It took me a while to figure this out, and I invented it. In our example, this is level 6, which is equal to 2k in general. And the secret is you go back until you find the last place you're in level k plus 1, which is equal to 4. And the reason for that is that 3 prime gained us k minus 1 Harvard wins in all. So what you do is go backwards to the first place where Harvard needs k minus 1 net wins in order to get to the final level. That gives you the dividing line between 2 prime and 3 prime. The dividing line between 1 prime and 2 prime, of course, comes right after the first game, and then you just reassemble these as 3, then 1, then 2. And to get 3, remember the deal is you traverse 3' backwards. So that's H, H, Y, 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 Y. Okay, I've now converted 3' back into 3. Then I have to do 1. 1' was a Harvard win, and 1 is therefore a Yale win. And finally, 2 is the simplest one, because 2 and 2' are exactly the same. And I've reconstructed the original path. And as I said, when I invented this, I was sufficiently unsure of it that I actually wrote a couple of functions in PHP that implemented this and tried out a number of cases to make sure that I got back what I started with in all those cases. Yeah, Robert?
I missed something. How did you pick out the border for section 1?
The border for section 1 is always section 1 is exactly 1 game long.
Always.
Yeah. Section 1 is 1 game long. The border between 2' and 3' is the tricky one, but once you have noticed that section 3' always gives Harvard K-1 extra wins, you can count backwards to the last place where Harvard needs K-1 extra wins. And the reason that works is that in the original split was we split between 3 and 1 game before Yale had its maximum lead. We split at the point where Harvard was K-1 games behind, and therefore we know that this has to give us back a net K-1 Harvard wins in order to take us from here to there. I will say, the details of this are not wildly crucial. The important thing to learn is, 1, these results. These results are worth remembering even if you have trouble reconstructing the proof, because they are so straightforward to remember and remarkable. And then the other important thing to remember is the general proof strategy. This is a very clever way of proving things. If you want to show that 2 sets have the same size, you don't necessarily have to count the number of elements in each set and write down some messy number that expresses this. It's sufficient to show that the 2 sets are in one-to-one correspondence with one another, and that shows they're the same size even if you don't know what that is. Have I got 1 minute left? Yeah. Classic example of this in the history of science. How many of you studied some chemistry? Okay. The classic example of this is the mole concept. The mole was around in chemistry for more than a century before anyone had managed to measure Avogadro's number. So don't believe anyone says the definition of a mole is Avogadro's number of anything. The definition of a mole is that quantity of anything that is equal to the number of carbon-12 atoms in 12 grams of the carbon-12 isotope. And chemists are clever enough to figure out when they've got 2 moles of oxygen from that definition. What they do is take 12 grams of carbon-12, they burn it, find out how much oxygen it has to combine with it to make all carbon dioxide, and they know that used up 2 moles of oxygen, even though they don't have a clue what the numerical value of Avogadro's number is. So this is an honored tradition in science. Okay, let's take a short break, and I will draw some even more remarkable conclusions from this. This has more points in it than the first one.
Okay. So
yeah, there's lots and lots of stuff you can do. And I think last year a couple of people found ways of getting more than 30 points total by inventing bells and whistles that I hadn't thought
I
of.
was going to say, on the first one, it seemed like you could kind of, if you could think of more distributions.
Yeah,
there's
sure.
A lot of distributions out there.
Yeah.
You could have gotten a lot.
Yeah. Basically, for any mathematical enhancement you put in if you want to claim 1 point more extra credit for it. I'm not going to argue with you. I may build it into the project description for next year, but I'm not going to discourage you. And to a certain extent, for user interface enhancements, I'm willing to give extra credit to. There's a limit to how much I'm going to give for using different fonts and different colors. But someone last year, for example, on the first project, found a way of displaying 4 distributions simultaneously on the screen in a 2x2 grid, which I hadn't thought of and which I thought looked quite elegant when it was done. Okay, are we ready to read? Robert, you've got a question?
I still haven't got anything to execute. Is there any way to get some help to figure out?
Yeah, I would think the simplest thing to do is to email it to me and then come over to Quincy House sometime, and we'll debug on my computer until we've figured out what the problem is. There's a remote possibility that there's something non-standard about your system that hasn't shown up, but enough people have done these successfully now that I think it's more likely the problem is, as one of my undergraduates discovered the other day, a missing semicolon or something like that. And I'm good at finding missing semicolons. Okay, so we're ready to get going, and we're going to get going with topic 13, which I've called Last Visit to Origin. So now I'm going to start reaping rewards from what I have just proved. And what I want to do now is consider a random walk that goes up, that goes down, passes through the origin a number of times, and then may take off anywhere. And this is going to be a random walk of 2n steps. Notice I am not assuming that the series is tied after 2n steps. And following the book's notation, I'm going to introduce the symbol t sub 2n to mean the last visit to the origin. That is the last instance where the series is tied. In a walk of 2n steps. Now, since I am going to be comparing paths that end up with Harvard way ahead and paths that end up with Harvard and Yale tied, equal numbers of paths in general don't mean equal probability. However, if I assume that Harvard and Yale are equally matched, so that I can assume the quantity we've been calling little p, the probability of a Harvard win is 1/2, then I can calculate the probability that we're in level 0 after a certain number of steps, and I'm going to call that number of steps 2m because in general it's not going to be the same as the 2n I've shown you here. And I'm going to denote that, as the textbook does, by u2m, and we can easily figure out a formula for that. For one particular path that's back in level 0 after 2m steps, we have 2m total games, each of which has a probability of 1/2 of coming out in accordance with one specific path. That is, if I draw a path like this that gets back to 0, and I want to know the probability of this particular path, one of the factors that goes in there is 1/2 raised to the 2m power. But now there are many, many paths that get back to 0 after 2m steps. Any path that involves M Harvard wins and M Yale wins will do this. So what binomial coefficient do I have to multiply by? 2m choose m. So this is the probability that if Harvard and Yale are equally matched and play 2m games, they will be tied after those 2m games. And here's what I want to show. What I want to show is that the probability that the last time that the series was tied was after 2k steps is equal to u sub 2k times u sub 2n minus 2k. In other words, I have a very simple formula for the probability that if I look back for the last tie, it happens after 2k steps. Notice I call these things 2n, 2m, and 2k because you can't have a tie when two teams have played an odd number of games. So if I go back to the previous display, this is what I am calling here last zero. If you look at the second one, for example, here's 300 steps, and if I go back, the last time that we were in level 0 was after 54 steps. Here the last time was after 244. Here the last time was after 52, and so on.
And those numbers are equal to 2m?
Those numbers are equal to those numbers are equal to 2k.
2k, right.
And so what I have now written down, though I still have to prove it, is incredibly a formula for the probability mass function for this number. I'm claiming that I have a formula that gives you the probability that if 2n equals 300, the last time the series was tied was after 244 games, after 252 games, and what have you. I have that simple formula. And not only do I have a simple formula, I have an incredibly simple proof. Here's the proof. You might think the next thing I was going to do was erase the board, but that's not so. How does this happen? Well, what happens is that in the first 2k steps, from here to here, Harvard and Yale futz around. Harvard may be ahead some of the time, Yale may be ahead some of the time, but after 2k steps, they're all tied up. And we have a symbol for the probability of that. That's what I called u sub 2k, right? Okay. Now, that's the last time they were tied, which means that in the last 2n minus 2k steps, there's never another tie. That's what I've called a non-zero path, right? Now, I defined u sub 2n, u sub 2m, to mean the probability of a path that returns to 0. But since the number of paths that return to 0 equals the number of paths that never touch 0 equals the number of paths where you never go negative, u sub 2n minus 2k is also equal to the probability that starting from this tie, one team or the other goes ahead and stays ahead forever. And that's the whole proof. I don't have to write anything more down. I'm saying this is obviously true because this is the probability that over the course of the first 2k games, Harvard and Yale end up tied, and this is equal to the probability that during the last 2n minus 2k games, one team or the other stays forever ahead, and therefore there are no more ties. Okay, everyone see that? And the secret of almost all these proofs is just knowing that the number of non-zero paths is equal to the number of return to 0 paths, and that therefore for two equally matched teams, the probability of a never tied again result is equal to the probability of a tied after that number of games result. Yeah, Jerry?
Just a minor detail. You expressed 2n and 2k as the steps and as the last visit, just to make sure those were even numbers, right?
Yes.
There's no
yes.
significance to k in itself.
That's right. That's right. Okay, now it's worth doing one numerical example of this, and then I'll show you the computer results. And if you get into this, some of you will be able to make prettier displays of the results than I did in my first crude attempt. But let's work out u sub 0. U sub 0 is equal to 1, okay? The probability of being at the origin in a random walk of no steps is 1.
It may be a good time to switch pens.
Thank you. U sub 2 is equal to, well, let's use the formula. 2 choose 1 times 1/2 squared. That's equal to 2 over 4, or 1/2. Everyone agree that's right? If you have a 2-game series, the probability that it's tied after 2 games is 1/2. The probability that one team was always ahead is also 1/2. That will happen if either Harvard wins the first 2 games or Yale wins the first 2 games. And furthermore, the probability that Harvard is never behind is 1/2. That means that Harvard wins the first game and either team wins the second game. So those things are all equal to U2. U4 is equal to 4 choose 2 times 1/2 to the 4th. That's equal to 6 over 16, which is 3/8. U6 is equal to 6 choose 3 times 1 over 2 to the 6th. That's 6 times 5 times 4 over 3 times 2 times 1 over 64, which is equal to 20 over 64, which is equal to 5 over 16. And finally, U8, which is the biggest one we'll need, is 8 choose 4 divided by 1 over 2 to the 8th. That's 8 times 7 times 6 times 5 over 4 times 3 times 2 times 1 over 2 to the 8th. 4 and 3 cancel the 8. 3 cancels that down to a 2. And that's 70 over 256, which is 35 over 128. And the reason I worked all these numbers out is that I want to show you a concrete numerical example now. The probability that t sub 8 equals 0, or the probability of t sub 8 equals 8. This is the probability that either the last time the series was tied was when it began, or the last time the series was tied was right now because the teams have just finished up in a tie, is according to my formula U0 times U8, which is 35 over 128. The probability that t sub 8 is equal to either 2 or 6. Let's get this right. T sub 8 equals 6 is equal to U sub 2 times U sub 6. U sub 2 is a half. U sub 6 is 5/16. And using the same denominator, that is 20 over 128. And finally, the probability that t sub 8 is equal to 4 is equal to U sub 4 times U sub 4. That's equal to 3/8 squared, which is 9/64, or 18 over 128. And if I plot this mass function, I get something that looks like this: 35, 20, 18, 20, 35. So this is, in the opinion of most folks who've thought about it, a highly counterintuitive result. Most people who know a little bit about probability and statistics say, yeah, the general rule always seems to be that things are most likely to come out in the middle. And I guess the same thing is true here. If you ask me when Harvard and Yale were most likely tied if they played 200 games, I would guess about 100 games ago. And look what's happened. The least likely time for them to be tied was halfway to where they are now. The most likely time for them to be tied is right at the beginning, and they were never tied again, or right now. Yeah, Jerry?
Think of it this way. The likelihood of two large streaks in opposite directions is fairly small, whereas the likelihood of one streak in one direction or the other, that is a lopsided series, is considerably larger, so that if you get one long run in a direction, you're not so likely to get one that balances out and get back to zero.
That's exactly right. Yeah, you're developing a better intuition for these. But the claim that's made is that if you show these graphs to the uninitiated, they'll say, there's something wrong with your random number generator. Your random number generator seems to have the property that once Harvard goes ahead, it stays ahead. Or once Yale goes ahead, it stays ahead. You've put something into it crooked that is, horrible term, violating the law of averages. Because can't you just hear the uninitiated saying that? Harvard is now 20 games ahead. According to the law of averages, Yale is sure to catch up. Stupid statement. According to Gambler's Ruin, if they keep playing, the series has probability 1 of eventually being tied. But there is nothing that says that if Harvard has got this far ahead, Yale is any more likely to pull the series down like this than Harvard is to push it up like that. And the net effect of this is that ties tend to occur toward the beginning or toward the end. Now, an interesting thing to do is a simulation on this.
I have a question. Why would they tend to occur toward the end?
That's a good question.
Yeah, it makes sense why they would occur towards the beginning, but what about towards the end? Because couldn't you extend the series after that to that?
Like, I'm just wondering what makes the end special. Because wouldn't that end just be the middle if we went further?
I'm afraid the best argument that I can give you is by the symmetry of the situation, the probability of last having been tied 6 games from the beginning is the same as the probability of having been tied 6 games ago, because in each case we have something that's equivalent to either coming back to tied or never touching 0 again for 6 games, multiplied by the same thing for 2n minus 6 games. But you see, the argument I give you is based on this incredible result that the number of non-zero paths is equal to the number of return to 0 paths, which I know it's true, but it's still not obvious to me why this is so. So you're right to be puzzled about this, because the proof depends on this crazy bijection, which establishes this highly counterintuitive result, and I don't think there is a simpler way to see it. Yeah, Catherine?
It seems to me that it would be less likely that there would be a tie 6 games ago as there would be 6 games from the beginning, depending on your position, because at the beginning you're starting at 0, but where we are right now is you could be at 20,000, and how could you be at a tie 6 games ago? You couldn't have been.
That's a good argument, but I think I've got a good answer for you. And the answer is these are 2 evenly matched teams. So at the end, the probability that they will be very close together is much higher than the probability that one will be 20 games ahead. You know, this is equivalent to the problem, you toss 300 coins, what's the probability of getting 152 heads or 154 heads? Answer very high. What's the probability of getting 180 heads? Much lower. And therefore, if you look at all these things, the ones that end up fairly close to tied at the end are much more frequent. And I think that's why it's not that unreasonable for them to have a recent tie in the tie. But the other thing is, I'm not saying that the probability is very high for the series to have been tied 6 games after the beginning. That's very likely. What I'm saying is that the probability of being tied 6 games ago is the same as the probability that the series was tied 6 games ago and it hasn't been tied since. And that second thing is the small probability. Okay? So I think that's why your intuitive argument isn't appropriate to the situation. I absolutely agree with you. The 2 teams started tied, and therefore the probability that they're tied 6 or 8 games into the series is rather large. I agree with that. But then that gets multiplied by the very small probability that having been tied at that point, they're never tied again over the next 292 or 294 games. So in both cases, we'll take the tied for the last time after 6 games or tied for the last time after 294 games. Tied for the last time after 294 games, we've got this rather large probability that after the 294th game there wasn't another tie, multiplied by the rather small probability that they were precisely tied after 294 games. In the case of tied after 6 games, we've got the rather large probability, u sub 6, that after 6 games they were tied, multiplied by the small probability, u sub 294, that there were no ties after that. And that's in exact agreement with the formula I had on the board. But the thing is, in both cases, the formula is the same, u6 times u294, but in interpreting the two, you have to interpret one of the numbers as probability of coming back to a tie, and the other one as no more tie. And it's because those two things are equal that these two things, which on the face of it sound different, come out the same. Now, I confess, I was sufficiently skeptical that I wrote a computer program to check this. So what I did was I generated 1,500 random walks, and what I did was to count the number of times the last tie was in the first 10%, between 10 and 20% of the way in, and so on, and look at the results. If you look at the first 10% or the last 10%, there's an enormous number of instances where that's the last tie. And this is not based on any theory. This is just I had the computer flip coins, basically, and I generated a lot of these, and I counted. And then if you look at the other ones, sure enough, the ones that are right smack in the middle are the ones that are least likely to occur. So this is borne out experimentally by a mindless coin flipping experiment, which suggests there is that while the theory may sound strange, it seems to be borne out by simulated experiment. Oh boy. Okay. I think I'll try with a different red pen. Okay. This is topic number 14, first visit to final. And there's nothing to this one. Got one of these random walks again. Harvard and Yale are playing and playing and playing again. And Harvard ends up a certain number of games ahead. And you can ask the question, how far into the series was Harvard first that number of games ahead? And this is exactly the same question that I just asked before, where I'm viewing the whole situation backwards and upside down. That is, the answer to this question is exactly the same, because what we have here is here's 2k. Since this is the first time that Harvard was its final number of games ahead, I didn't introduce a symbol for that. And drawn this sloppily. This path must be all on one side of this line. Okay? And it could be all on this side, it could be on the other side, depending on whether Harvard ends up behind or ahead in the series, but it can't touch this line again. We know the probability for that to happen is u sub 2k, right? That's a generalized statement. You start at any level, proceed through 2k steps. The probability that you never return to your original level in those 2k steps is this quantity u sub 2k. And then Harvard is a certain number of games ahead. It ends up the same number of games ahead. So we have 2n minus 2k steps, in the course of which Harvard and Yale win equal numbers of games. We know the probability for that is u sub 2n minus 2k. So the distribution for the first occurrence of Harvard's final lead is exactly the same as the distribution of the last visit to the origin. And sure enough, when I plot up first final, I get the same sort of numbers. These don't agree perfectly. That's because I only ran 1,500 trials. The reason I only ran 1,500 trials is that PHP was timing out on me after 30 seconds, and I couldn't find where in the configuration file to change the timeout number. You can probably figure that out and run more if you want. But certainly, this is enough to make me feel comfortable in the statement that the probability mass function for this is the same as the probability mass function for that. And notice how looking at real-world numbers, at which point you're doing statistics rather than probability, makes life much more difficult. When you look at real-world numbers, you have to say, the frequencies are not going to agree with my probabilities. I can calculate the probabilities exactly to any number of decimal places, but if I do only a finite number of experiments, all I can hope is that the frequency of occurrence of each outcome is not too different from its probability, and it would be nice to know the probability of being off by a certain amount, which I'm going to do in the last class in January. So that's all there is to number 14, first visit to final. So I can go right on to number 15. Final visit to max. And put the note messy. Forget it. Because there's some complications involving the first case, the case where the maximum value is Harvard and Yale are tied, and then things go downhill from there. And the general formula I stated in the notes is correct except for the case 0. In this simulation, that doesn't make much difference, but in any simple example I could do, it screws everything up. So all I'm going to tell you is that the same general sort of result works here. That is, Harvard gets ahead by a certain amount and never gets farther ahead. And if you ask, what's the probability that Harvard is its maximum of 2 M games ahead after 2 K games have been played, the answer is 1/2 times u sub 2k times u sub 2n minus 2k, exactly the same function as before. And the argument is basically this. This is the maximum. Therefore, this has to stay on one side of it, and this has to stay on one side of it. And this is reflecting the probability of staying on one side. This is reflecting the probability of staying on one side. And the 1/2 is for the fact they either have to be both below or both above. And that's all I want to say about this. I mention it because it's plotted here and because I'm encouraging you to work this statistic out in your own version of this. And you can see it more or less agrees, but the number here is anomalously high because some of the probability that should be in here ends up in there because the general formula assigns a value for 2n plus 1, which really belongs in 0. And I just don't want to get into this mess. So forget I ever put it in the outline. All I want you to do is to know this, that this same sort of universal function also applies to this case. Okay.
Well, the outline says first visit. Are they equivalent?
First visit to max.
Final.
Oh, the outline is correct, and I was wrong. Thank you, Sue. This is first visit to max, not final visit to max. That was just careless on my part. So the first visit to max, which I've put in my program as first max, is the one that I want. And the formulas in the notes are correct if you want to check them, except for the value 0. The value 0 for 0 is double what's given in the notes. And fixing that up makes the proof so messy, it's really not worth our time. Because there are equally interesting results that are easy to prove. So here's the next one. This is number 16, which is first return, by which I mean the question that I want to answer is, what is the probability that after 2 endgames, Harvard and Yale are tied for the first time since the series started? And remarkably, there are 2 extremely simple formulas for this. So, following the book's notation, I'm going to introduce the symbol f sub 0 of 2n, and this means the probability that the series is tied for the first time after 2 endgames, or more generally, that a random walk has returned to level 0 for the first time after 2 endgames. Now, here's the first formula for this. This is equal to u sub 2n minus 2 minus u sub 2n. And this is proved in the book using binomial coefficients. Sturzacher doesn't write out all the algebra, but I'm sure he does all the factorials right. It's about two long lines of messy algebra. And I looked at this and looked at this and looked at this and thought, there has to be some way that this was obvious. And eventually it hit me during a long car drive or something like that. Yes, this is obvious. It takes about 30 seconds to explain why this is so. And the reason it took a while for it to be obvious is we have to interpret both of these as the probability of not touching 0 again, of no ties. So if Harvard and Yale are going to be tied for the first time after they've played 2 endgames, what has to happen during the first 2n minus 2 games? No ties in the first 2n minus 2 games. Right? So this is the probability that this sort of thing will happen. Okay, now, after 2n minus 2 games, the series hasn't been tied. We want it to be tied for the first time after 2 endgames, and therefore we want to subtract out from this probability the probability that the series still hasn't been tied after 2 endgames. So this is no ties in the first 2n minus 2. This is no ties in the first 2n. And if we take the probability that there are no ties in the first 2n minus 2 and subtract from that the probabilities that there are still no ties after 2n, we have the probability of the difference of the two sets, namely the probability that there were no ties in the first 2n minus 2 games, but there was a tie after 2 endgames. So that proves this formula. As I said, it took me several hours of thinking to find the simple explanation of this, but I claimed I was going to do this all nice and non-computationally. There's another formula for this. It's amazing that these two formulas agree with one another, but they do. Another formula for this is it's u sub 2n over 2n minus 1. And I have a simple proof for that one, too. Okay. How can you have a tie after 2 endgames? Answer is after 2n minus 1 games, the teams are separated by exactly 1 game in the standings. And then in the very last game, the series gets tied. So the probability of being tied after 2n games is u sub 2n. That's how I defined it. That includes the possibility that they were tied lots of times before that. So they start here. They play 2n minus 1 games. According to the ballot theorem, in what fraction of the cases do we have something like this, where the team that's 1 game ahead after 2n minus 1 games was always ahead during that? 1 over 2n minus 1. So this comes from the ballot theorem, and that completes that proof. So I told you that once you have this basic counterintuitive result that the number of non-zero paths equals the number of return to 0 paths, you can get corollaries galore out of this. And the next one is, this is something I just discovered during the final revision of this outline before I passed it out to you. I was trying to come up with a cleaner version of the book's proof from topic 18, which is going to be called Strange But True, and I decided it was a good idea to split off the key new result in the proof as a separate topic, and it suddenly hit me, hey, here is another thing that's equal to u sub 2n. I had never realized this before. We can ask the following question. Harvard and Yale play 2n games. What is the probability that they are tied once and only once during those 2n games? So this is topic number 17, returning just once. And I'm interested in assessing the probability of this sort of thing. We'll let Yale go ahead at the beginning. Yale goes ahead. Harvard ties the series. And then it's never tied again. What's the probability that we have a series like this where there is one and only one instance after the start of the series where the two teams are tied? So let's suppose that happens after 2k steps. This has to be a non-zero path here, doesn't it? Because if it weren't a non-zero path, there'd be a later tie. and the number of non-zero paths is equal to the number of paths that return to the origin, right? And therefore, for any path like this, I can, by a well-known algorithm, construct a path that returns to the origin. If the first tie occurs after 2n games and not before, then these two things are one and the same. But in general, I have to convert a non-zero path into a return to zero path. And that means the number of paths that are tied after 2k and not tied again are equal to the number of paths that are tied after 2k and still tied after 2n. That's the number of paths that are tied after 2n. So this is equal to u sub 2n. And this one is actually worth working out. So let's look at the 4-game series. With exactly one tie. Okay. Let me remind you what U4 is equal to. U4 is equal to 4, choose 2, times 1 over 2 to the 4th. That's 6 over 16, or 3 over 8. So out of the 16 ways for this series to come out, this predicts there are 4 ways that it can be tied exactly once. And here they are. Harvard wins the first game, Yale wins the second game, and Harvard then goes ahead. Harvard wins, Yale wins, and Yale goes ahead. Yale wins then Harvard to create the tie. Harvard wins the last 2. Harvard wins, then Yale wins, and Yale takes the last 2 games. And finally, there are the cases where Harvard wins 2 and Yale wins 2, or Yale wins 2 and Harvard wins 2. And these are the 6 ways that that there can be exactly one tie somewhere during the series. And that's what we need for the very last of these topics. How much time have I got on this? I got about 15 minutes, which I think is slightly more than I need, for the result that the book calls strange but true. And this is one of the very few results in our textbook that isn't in the more advanced book that Sturzacher co-authored with Jeffrey Grimmett, which I use as my text in Math 191. This really is a strange result, and I hope I can convince you that it's true. So, here's what we've got. Strange but true. We have a random walk and we'll use the Harvard and Yale football model again. And you might say, okay, this is reported daily in the newspaper, and every day they say Harvard is so many games ahead or so many games behind. If I tally all these things up, what is the expected number of values of games behind that occurs exactly once? That is, there was only one time during this entire series that Harvard was exactly 3 games ahead, or exactly one time that Harvard was exactly 5 games ahead. And the answer is, no matter how long the series is, the expected number of win differences that occur once and only once is 2. So we've got a random walk, V sub n, the book's notation, is equal to the expected number of levels reached exactly once. And the claim is that V sub n equals 2, and the proof is by induction. Okay. We need a base case. Here's the base case, a one-game series. At the start of the series, it's tied and Harvard is 0 games ahead. That happens once. After the game has been played, either Harvard is 1 game ahead or Yale is 1 game ahead, and that happened once. So we have a one-game series. There are 2 score differences. Each of them occurs precisely 1 time, and the expected number of score differences that occur just once is clearly 2. Everyone comfortable with that? Okay. Now what I've got to convince you is that if this result is true for a series of n-1 games, it also has to be true for a series of n games. And this is the same argument as in the book, but I hope that my explanation of it is a little bit clearer than the one in the book. So my inductive hypothesis is that V sub n minus 1 is equal to 2. And if making this assumption, I can prove that V sub n is equal to 2, then I finished off the proof. And here's how I propose to do it. Let's, without any loss of generality, look at a series where Harvard wins the first game. Exactly the same argument applies if Yale wins the first game. And what I want to do is look at this whole random walk but ignore the first step. So here I have n minus 1 of my n steps starting after the first game. Now, for these n minus 1 steps, ignoring the first game, what am I entitled to assume is the expected number of levels achieved exactly once? 2, by my inductive hypothesis. So if I can show that when I put the first game of the series, this Harvard win on, that expectation doesn't change, I prove the result. Fair enough? Okay, now what can happen? There are 3 things that can happen. And I think I'll put these up here. Three things can happen when we add the first game. And I'll use what I think is the correct verb, prepend the first game. Well, one thing that can happen is when we put the first game on, we insert the one and only instance of a tie. And for what sort of series will that happen? For what sort of series will we have a tie only before the first game has been played? A non-zero path, right? So if we have a non-zero path for 2n games, this adds 1 to V sub n, because we have the expected 2 levels that were achieved only once, and then we've got this level 0 that was also achieved only once. Okay. Can anyone see a circumstance under which we will decrease the number of levels achieved only once by putting this tie at the beginning? Remember, we're counting the number of levels achieved only once. If we already had a level achieved only once and then put it in for the second time, that will decrease the count by 1. So if we had exactly one tie, in 2 endgames, then putting in the extra tie from the start will change 0 from something that was achieved only once to something that was achieved more than once, and therefore it will subtract 1 from V sub n. And finally, anything else, namely ignoring this initial tie, the series was tied more than once, this level was already achieved more than once, and adding this will make no difference. Okay, so in some cases we will add 1 to V sub n. In other cases we'll subtract 1. And the question is, which is more likely? Well, what are the comparative probabilities of having a series that is non-zero over the first 2 endgames and a series that is tied precisely once over the first 2 endgames? As I've just shown you, those probabilities are exactly the same. And fully on all the algebra in the book. That's the whole proof. Once you know that the probability of having exactly one tie is the same as the probability of never being tied at all, you say, okay, we've got this expectation, and the probability of increasing it by 1 and the probability of decreasing it by 1, where we put the first game back in, is exactly the same, and therefore it doesn't change, and therefore, since it's equal to 2 in the base case, it's equal to 2 forever. And that's it for random walks. Next week, I'm going to talk about generating functions just a little bit and show you how you can compute amazing things like the probability of throwing a total of 26 on 10 dice in terms of simple calculations involving binomial coefficients. And then after vacation, I will prove a couple of laws of large numbers, and you folks will all be very well grounded in discrete probability theory then.